This video is about making custom circuits directly with microcontroller chips, which can still be programmed with Arduino. Whilst Arduino boards are designed to help people learn Arduino, our own projects have different objectives, often with different size, shape, cost, or power supply requirements, which are much more easy to fulfill if we integrate the chip directly in our design rather than through an Arduino board. As we will see in this video, it's often easy to support a microcontroller in a circuit, and with a few additional elements, it's possible to enable it to be programmable with Arduino whilst in circuit. In this video, we'll start by looking at how the Arduino system works with Arduino boards and why, and from there determine the minimum elements necessary in a custom circuit so that it fits in this system and can be programmed by it. We will then look at a practical example, a simple circuit which works as a minimalist Arduino Uno and which can be used as a base design for more complex circuits around this microcontroller. We will look at how you determine which additional components are necessary in the circuit for this microcontroller, its configuration options, and its power supply requirements. We will then look at how you can configure it and program it in the Arduino IDE, including an explanation of the various configuration options you can see there. Whilst you can jump to the second part of this video, it is highly recommended that you watch the first part as it provides an overview of how to design custom circuits for compatibility with Arduino. Future videos will cover areas related to this domain, such as, for example, voltage regulation, alternative Arduino development environments, and other microcontroller families and even architectures. To use Arduino with our own electronic circuits, rather than with pre-made Arduino boards, we first need to understand the various parts of Arduino and how they work together, so that the circuits we design fit in that system. For that, we will first look at the Arduino system at an architectural overview level, high enough to see blocks and flows whilst not spending too much time in details. The Arduino architecture is more easily understood if you think of it as having three big blocks. On one end, running on a computer, is the Arduino IDE and auxiliary applications it uses to build, upload, and monitor our programs. On the other end is the Arduino board itself, which is the piece we want to replace. Between both is the Arduino core, a software library on top of which Arduino applications are developed. The Arduino IDE is a software development environment for making Arduino applications. It provides an environment for coding programs and uses other pieces of software to compile them for specific microcontrollers, upload the resulting binary programs to the boards, and monitoring messages from the boards. Because of this structure, the Arduino IDE can be extended with support for different boards, including custom circuits, and for uploading the software in different ways. Other software, such as Platform I/O, also let us make Arduino applications following similar principles, but we will not go into those in this video. The Arduino core is a software library which allows development of applications for microcontrollers using a standard set of functions and objects which hide the details of how things are done in each type of microcontroller. Without an Arduino core, to develop programs for a type of microcontroller, a person first needs to learn a lot of information specific for that type of device. Further, third-party libraries made for one type of microcontroller without using something like an Arduino core do not work on another type. When making our own circuits with microcontrollers, the use of an Arduino core means that all that we learn about programming with Arduino directly works for our own circuits, and also that most third-party libraries done for Arduino will work in those. Most of an Arduino core is the implementation of the Arduino functions and objects for a specific microcontroller type. However, a core also includes an additional layer of configuration hidden from our code, which is board specific and tells the Arduino IDE things such as which microcontroller pins are mapped to which Arduino pins on the board, which of those support analog access, the location of pins for things such as SPI and so on, as well as containing instructions to the IDE about available build options and how to call auxiliary applications for building and uploading programs with those. When for the same microcontroller you see several Arduino core implementations, the reason is almost always the presence of different or additional board configurations, as the code implementing Arduino core functions and objects, which depends on the target microcontroller type, is the same or very similar. Fortunately, for makers of custom electronic circuits who want to use Arduino, such as us, there are Arduino cores for many microcontrollers containing board configurations which map directly to the microcontroller pins, so we need not worry about Arduino core configuration until reaching some very advanced microcontrollers. Arduino boards are electronic circuits designed with the purpose of helping beginners learn the development of microcontroller applications. This is why, as you see here, they have not just a microcontroller, but also a means to connect to a computer, a simplified upload process via that connection, a built-in generic power adapter, and other hobbyist-friendly features such as a precision clock and various signaling LEDs. This is also why they're designed to get power from the computer via USB. On the other hand, generic electronic circuits with microcontrollers, the main subject of this video, are designed for other specific purposes. Whilst both types of circuit share the presence of a microcontroller, the other elements present in Arduino boards are usually not needed and not included in the generic ones, as they would add cost, take extra space, increase circuit assembly time, and even hinder the main purpose of that circuit, for example, by consuming too much power. We will see in more detail how the traditional Arduino board works in the following two diagrams. This is the build and upload process with the traditional Arduino board. You can see how the Arduino IDE uses other applications to build the microcontroller program from the source code and Arduino core and then sends the resulting binary program via USB to the board. On the board side, a USB to serial adapter makes the communication reach the microcontroller via a protocol it understands, UART, known in Arduino as serial. In the microcontroller, a small program called a bootloader is running, which understands the upload commands coming in via serial and which then stores the program being uploaded in the microcontroller's program memory. Bootloaders are pre-installed in the microcontrollers of Arduino boards. They run immediately after power up or reset and check for updates for a few seconds, passing control to any user programs already in memory after that time. This is why, if you have a program in an Arduino board, after power up or reset, it always takes a few seconds before that program starts. Notice that during this stage the Arduino board is being powered from your computer via USB, which includes a 5-volt power line, and that if the microcontroller requires a different voltage, the power adapter on the board itself is used to convert those 5 volts into the appropriate voltage. In some Arduino boards, the microcontroller used directly supports USB, so the board does not have a USB to serial adapter and the bootloader works with USB directly. Here you can see the runtime operation with a traditional Arduino board. In this phase, our program is running and the hardware we added is being used, but all the other hardware and software elements in the Arduino board used during uploads are at most used to pass debug messages to the computer, something only needed during development and not usually for normal operation. Notice that power is still coming from the computer, so the circuit has to be physically connected to one. Whilst Arduino boards can be used with other power sources, almost all boards waste too much power for things such as operating from solar cells or using batteries as a long-duration power supply. Also notice that the bootloader is present and using microcontroller memory, but is not used or useful during normal operation. In the next 2 slides, you can see how a custom circuit can work in the same 2 stages. In this first slide, you can see the normal operation with a custom electronic circuit. The microcontroller is still there, as is the part of Arduino we want to continue to use, the core, but the software and hardware supporting the Arduino specific upload, as well as the beginner-friendly hardware, are gone. What is left is a circuit with only those hardware and software elements necessary for normal operation and for which we now have to provide our own power source. Connectivity to the monitor in the Arduino IDE during development can still be done, but must now go through an external serial adapter connected to the microcontroller serial pins, an optional element which is reusable and temporary. A precision clock, signaling LEDs, or even power adapter can still be part of the circuit, but their presence and characteristics are now according to the needs of our project rather than being set in stone as part of a board. So, how can we upload our programs into a custom board if it has no connection to a computer? First, you need to understand that the normal Arduino upload process is not a standard program upload process for microcontrollers. It's an Arduino-specific upload method, which is why it requires that the bootloader is pre-installed in the microcontroller before it works. With a custom circuit, the way we upload a program to a microcontroller is using the standard upload process for that microcontroller, which is defined by the manufacturer as part of the microcontroller hardware itself and thus works straight out of the factory without any bootloader having to be installed in it. This is why, in the diagram, you can see that the only required parts in a custom circuit for upload are the microcontroller itself and the components it requires in order to operate. Further, you can also see that there is now something outside our circuit called an external programmer, which connects directly to the microcontroller in it on one side and to our computer on the other. The external programmer is a standalone device which can upload programs directly to a microcontroller. As the Arduino IDE already supports several external programmers and can be made to support more, we can still use it to develop programs for our custom circuit, as it will compile and upload our programs, only do so via the external programmer rather than directly to the board. Unlike with the Arduino upload method, different families of microcontrollers sometimes require different external programmers, although cheap and even homemade versions of these are commonly available. Because an external programmer can also provide power to our board during the upload stage, no other power source for the board is required. In engineering, the design of a device or system is based on what is required for its normal operation. And whilst for an Arduino board, the uploading of applications to the microcontroller is a frequently executed normal usage scenario in a generic device, such as, for example, a Pong game device, that is not the case. Hence, what is required by both being very different. When designing a custom circuit, we will put in the circuit only the minimum required to allow uploading, as that is not part of its normal operation. Circuit elements of an Arduino board, which are there to facilitate board programming and uploading, because that's part of such board's normal operation, will not be in a generic circuit, so it's a much simpler circuit. In our example, the Pong gaming device, it will have a microcontroller, a screen, control buttons, and a buzzer, as well as our software for it. But no USB connector, no USB to serial adapter, no bootloader, no serial transmit or receive signaling LEDs, and, in general, no hobbyist-friendly elements used only during upload. In a custom circuit, the complex hardware and software needed for uploading is outside our circuit in the external programmer. Because of the use of an external programmer, it is often the best choice to include in the circuit design a connector for it to have easy access to the microcontroller for programming, as you can see in our example circuit. Note that the Arduino Uno board also includes exactly that same connector for the same purpose, as that is the only way to install or update a bootloader without removing the microcontroller. In the next segment, we will talk about a simple microcontroller circuit with Arduino. We will look at not only the how and why of the circuit design itself, but also at the process of developing and uploading programs to such a circuit. Here is a simple circuit containing just a microcontroller and the minimum parts it requires to run, and which can be used as the microcontroller core in more complex circuits. As per the design principles explained in the previous part of this video, this circuit can be programmed from the Arduino IDE using an external programmer, a device which is specific to each family of chips. So for this project, we chose a microcontroller for which the external programmer can easily be made at home from an Arduino Uno, Nano or Mega board. This circuit, although designed from scratch around the microcontroller, as we will explain, is essentially a minimalist version of an Arduino Uno or Nano board. So the programs we can run in those boards can be run in this simple circuit. To illustrate that, here is a simple example where we added a small OLED screen to our base circuit and uploaded to the microcontroller a sketch that just displays some text on that screen. The design of a circuit like this starts by choosing a microcontroller for which there is an Arduino core and which fits other requirements of our project. This specific project should be a simple example, a starting point for further learning, and be useful as a microcontroller-based circuit
when designing full projects, so we require a microcontroller which is cheap, so that even the biggest mistake isn't painfully costly, fits on a breadboard, so you can try things out with it and easily prototype your full circuits on a breadboard first before making a PCB or soldering any components, is simple to start using so that you don't lose time just getting the microcontroller to work and can focus on the rest of your project, for which an Arduino core exists that works directly with chip pins so that we don't need to change the code and configuration of an existing Arduino core, and which is commonly used with Arduino in boards and as a standalone chip, so that there is a lot of information about using it on the internet. So we chose the 80MB 328 microcontroller used in the Arduino Uno and Nano boards in a chip package called TIP, which can be plugged on a breadboard or soldered on a perf board. When ordering this chip, you will see that there are a number of minor variants of it, such as the 328P and the 328PA. All except the 328PB variant will directly work in this circuit and can be programmed in the same way. Further, the full code of this microcontroller chip includes some letters for the type of chip package, and the DIP package is the one with the code ending in -PU or -PN. So those are the ones you want to try out this example on a breadboard. As we are currently in a period of semiconductor shortage, it might be hard to find this specific microcontroller. This needs not be a problem, as you can use in this circuit other microcontroller models of the same family with a bit less memory, such as the 80MB168 and 80MB88. They have the same DIP package with the same pinout, can be programmed in the same way, work in the same way, have similar minor variants, and just differ in that they can't fit quite as large programs, which is not a problem at all here, as we use the blink sketch to check that our circuit is working, and that one easily fits even the smaller of these models. In order to determine how to use most microchips, including this microcontroller, datasheets are essential. Hence, we will be using the information from this microcontroller's datasheet in designing our circuit and determining how we use it and how we upload programs to it. Datasheets for microchips can usually be found by searching on the internet for the word datasheet and the chip's model code. But to make things easier and avoid confusion, we provide an URL for the datasheet of this microcontroller below the video. As explained in the Arduino system overview, in order to support Arduino in a microcontroller, we need an Arduino core for it. So we will need one for this microcontroller. Whilst there are various cores that support this microcontroller, we will use one called mini core, as it works directly with the chip itself by having the Arduino board be the chip itself. So, Arduino pins and functions are mapped to the pins of the chip. The URL for the Minicore website is below, along with a direct URL to the instructions on that website for installing that core in the Arduino IDE. You should also get the pinout diagram for this core and this microcontroller from that site, as that diagram is the fastest way to find the Arduino pin numbers and functionality for each chip pin. With the pinout diagram on hand, we can see that the connections in our circuit are done following a simple logic. There are two pairs of power supply pins, one on each side of the chip, where the VCC or AVCC pin expects the positive power supply line and the GND pin expects the ground line. So we connect those pins to the matching power lines. There is also a pin used for the analog voltage reference called AREF. The microcontroller manufacturer recommends that if we do not use an external analog reference, we connect that pin to the positive power supply line, so we connect it as recommended. We now need to look at the additional components we need for this microcontroller to work. So at this point, it's a good idea to talk about decoupling capacitors. Microcontrollers and other complex digital microchips such as this are made from hundreds of thousands or even millions of microscopic MOSFET transistors and typically execute millions of operations per second. Because of this, they can have random and very fast spikes in power consumption, which exceed the response speed of the main power supply. When, during such a spike, the extra power being demanded does not arrive from the power supply fast enough, the voltage on the chip supply pins can drop below the minimum required voltage and the chip can malfunction. So, for stability, most digital microchips require decoupling capacitors placed next to the power input pins of the chip, which work as tiny local stores of power that quickly compensate for any power demand spikes during the time it takes for the main power source to respond. If you've ever seen the electronic circuits of the most complex digital microchips, such as microprocessors, you have probably noticed many surface mount capacitors right next to the microchip. All or almost all of those are decoupling capacitors. When designing a circuit with a digital microchip, to find the recommended characteristics, locations and values of external components required by it for stable operation, such as decoupling capacitors, we would normally check its datasheet, but for the family of microcontroller chips we use in our circuit, that information is in a separate document which covers a large part of that manufacturer's range of microcontrollers and which is called Application Note AN2519. You can find it in the manufacturer's website or follow the URL provided below directly to that document. From that application note, as expected, we get the recommendation to use one capacitor for each power input pair, with the analog power 1, the one connected to the AVCC pin, being explicitly specified as a 0.1 microfarad ceramic capacitor. As no actual value is specified for the capacitor for the digital power pin pair, we go with the choice of capacitor value which is commonly used for this function for microcontrollers, which is also a 0.1 microfarad ceramic capacitor. This is how we ended up having two 0.1 microfarad ceramic capacitors, one for each power supply pin pair, connecting the pins of the pair right next to him. When doing your own circuits with other microcontrollers and even other complex digital microchips such as signal generators or display drivers, you can follow the same process to discover the needed extra components, and often the exact circuit with the exact component types and values needed for that microchip to function correctly in a circuit can be found in its datasheet. Note that this application note provides information for additional components to use with these microcontrollers. However, as we are not using an external clock, what we call a precision clock in the Arduino overview section, and instead use the microcontroller's internal clock, and as we are not providing a reset button, we do not need the components mentioned in those sections. Now that we have the necessary parts and connections in place, we need to find out how we can power this circuit. For that, we need to figure out the power supply requirements for this microcontroller, so we check the datasheet for it. First, we find in the summary information on page 2 that this microcontroller has an operating voltage range between 1.8 and 5.5 volt, with narrower voltage ranges for something called speed grades. Further details for this are found in the electric characteristics section of the datasheet. The first thing we find there is the absolute maximum current the microcontroller can consume, 200 milliamps. So, to be on the safe side, our power source should be able to provide at least this much current. We can also see that the absolute maximum voltage is 6 volts. This value is the maximum voltage the chip can be exposed to without being damaged, but is not a voltage the chip will reliably operate with. Going a bit down to the speed grade section, we find that the clock speed the microcontroller is running at can require a higher minimum voltage than the absolute minimum for this chip. The higher the clock speed, the higher this microcontroller's minimum operating voltage is. In our case, we are not using a precision clock and instead use the internal oscillator of this microcontroller at its maximum speed, which is 8 MHz. So that is the speed the microcontroller will run at. Looking at the diagram in that section, we can calculate that for a speed of 8 MHz, a minimum voltage of 2.4 volt must be supplied to the microchip. Putting it all together, the datasheet tells us this microcontroller is guaranteed by the manufacturer to work at 8 MHz as long as its power supply makes available at least 200 milliamps of current with a voltage between 2.4 volt and 5.5 volt. This is why supplying this microcontroller directly from 2 AA batteries, which adds up to 3 volts, or 3 AA batteries, which adds up to 4.5 volts, works fine, as does powering it using a 5 volt wall socket power supply or from a USB connection to a computer, which includes a 5 volt power line, as done in the Arduino boards. All of those power sources have a voltage in the required voltage range and can provide enough current, so no adapting of power is required in the circuit itself. When designing a circuit, remember that the required voltage and maximum current drawn by any microchip you are planning to use can always be found in its datasheet. At this point, we have the circuit design done. We also know that we can power it directly with two AA batteries, so that's what we will use. As you can see, the circuit design turns out to be very simple. In order to be able to make Arduino applications and upload them into the microcontroller in this circuit, we need to install Minicore in the Arduino IDE and to make an external programmer that can upload programs to this microcontroller. First, if you have not done so already, use the URL below this video to go to the installation instruction pages on the Minicore website and follow the Arduino IDE installation instructions there to get that core installed in your IDE. With that core added to the IDE, a new group of boards called Minicore becomes available under the Board menu, and after selecting the ATmega328 board, the Tools menu will show all the options available for programming that microcontroller family via this core. To upload programs into the microcontroller in this circuit, we will use a protocol called Encircled Serial Programming, also known as ICSP or simply ISP, which is a manufacturer protocol for uploading programs to chips from this family of microcontrollers. This protocol does not require a bootloader because the microcontroller chip directly supports it in hardware. And in fact, one of the ways bootloaders can be installed in this type of microcontroller is via this protocol. We can make our own external programmer device for ISP chip programming by uploading to an Arduino Nano, Uno or Mega board a sketch from the Arduino IDE examples called Arduino as ISP. Once we have one of those boards with that sketch installed and thus working as an Arduino as ISP programmer, we can proceed to program the microcontroller in our circuit. To wire the programmer, we use the pinout diagram we got from the Minicore website to find the SPI pins called SCK, MISO and MOSI and the reset pin on the target chip. We then connect each SPI pin of our homemade programmer to the pins for the same SPI line on the target microcontroller chip. Next, we connect the Arduino pin 10 of our homemade programmer to the reset pin of the target chip. Since the Arduino user's programmer runs at 5 volts, the microcontroller we are using should also be running at 5 volts, since the voltage of the signals coming from the programmer should not exceed the voltage that the target microcontroller chip is running at. The easiest way to assure that is to source the power for the target microcontroller chip from the 5-volt power pin of the homemade programmer. So we connect the 5-volt pin from the programmer to the positive supply rail. As is always needed when connecting to circuits, the ground of the programmer gets connected to the ground of the microcontroller. Notice how in the Arduino Uno, Nano and Mega all the chip programming lines are available along with the power lines from a 3x2 connector. This is not by chance. This is the ISP connector used to upload a bootloader to the microcontroller in those boards in the very same way we are programming our microchip. When programming another chip, the Arduino as ISP sketch in our homemade programmer uses all of those very same lines, except reset, as outputs, so we can get all those outputs from the ISP connector in our homemade programmer board and get the target chip reset connection from the programmer's Arduino pin 10. In fact, when designing circuits with this type of microcontroller, if we intend for the microcontroller to be programmable after installed in a circuit, it's often a good idea to add an ISP connector like this to our circuit design, not just for convenience, but because professional ISP programmers are designed to plug to such a connector. In the application note we mentioned earlier, there is a section about these programming connectors, which includes the pinout for this ISP connector. At the end, you should have wires from the programmer to all three ISP pins of the target microcontroller chip, as well as one to the reset pin. You should also have wires connecting the programmer power pins to the power rails for the microcontroller chip on the breadboard. With the connections now done, before we can upload programs to it, we must first configure the microcontroller chip for the circuit conditions it will run in. Most importantly, the source and frequency of the clock it will be running with. For this family of microcontrollers, this is done via what is called burning fuses. Once burned, the fuse configuration is retained after power is removed, but burning fuses is not an irreversible operation for all but the few special fuses which we won't touch, and we can burn fuses again on the microcontroller chip if we want to change the configuration. Burning fuses is done in the Arduino IDE as follows. Under any sketch, as the sketch isn't important, open the Tools menu and make sure the board is set to 80MB328, a setting which is under the Board/Minicore menu. After that, in the Tools menu, set the following options. Clock to internal 8 MHz, which is the highest internal clock we can use. You can see that there are external clocks available as options here, but those require what we earlier called a precision clock, which is a crystal of that frequency and the load capacitors for it. Precision clocks are needed when precise timings are required, such as for high-speed serial communication, which is not the case here. BOD set to 2.7 volts. The brownout detector is a system in the microcontroller which will keep it reset when the supply voltage is below the value set here. Without BOD active, the microcontroller might operate incorrectly if the supply voltage falls below the minimum required, for example, due to almost empty batteries. As the minimum power supply voltage required for this microcontroller running at 8 MHz is 2.4 volts, we set the BOD level at 2.7 volts, which is the first value available above the minimum required voltage. EEPROM can stay as is. We can have the EEPROM be erased anytime a program is uploaded to this chip, or we can have the values in it preserved. Since we don't use EEPROM here, we don't really care either way. Try to enable compiler LTO, which will not be possible in older versions of the Arduino IDE. Compiler LTO makes your programs smaller by more efficiently removing unused library code. It is not required for use here, even if using an 80MB88, since we test our circuit with the Blink example, which is a very small program, but can help fit larger programs in a microcontroller. Make sure the variant is the same as the chip you are using, for example 328P or 328A. As bootloader, choose No bootloader. It's possible to choose to install a bootloader here, but we don't need one as we are using ISP for programming, not the Arduino specific protocol, which is the one that requires a bootloader. Because we don't need one, installing a bootloader would just waste memory and make the microcontroller startup times longer. For programmer, choose Arduino as ISP. Notice in this menu the many more external programmers supported by the Arduino IDE just for this microcontroller. Now execute burn bootloader. This both burns the fuses of this microcontroller chip with the configuration we defined in the tools menu and would, if we had chosen to have one, upload a bootloader to it. If it all ran well, the microcontroller will now be configured. If it did not and you see an error in the log, the problem is usually in either the connections to the chip or the wrong COM port having been selected. Make sure the connections are correct and that you have selected the COM port of the homemade programmer, as that's the device the IDE talks to directly when uploading your program to the chip. After the fuses have been burned in the microcontroller chip, we can upload programs to it using the homemade programmer with exactly the same connections and Arduino IDE configuration as we used to burn the fuses. At this point, the circuit is complete and the chip is configured, so we can simply open the Blink sketch from the Basic Examples menu in the Arduino IDE and, with the same IDE configuration, upload it to the chip as we would normally do to an Arduino board, after which we should have the Blink program running on the microcontroller. To actually see that there's blinking, we need to have an LED connected to the Arduino pin 13. Looking at the mini-core pin-out diagram, we find that Arduino pin 13 is mapped to the chip pin 19, the same one to where we connected the SCK line from the programmer. The LED positive side should go there, the other side to a resistor of at least 200 ohm and the other side of the resistor to the ground rail. With this additional hardware in place, we can now see the LED blinking. If we change the delay values in the program in the Arduino IDE and upload it again, we can see the blinking has the new timings. This simple circuit we put together here is the basis for all manner of circuits using this microcontroller as their brains, such as our example Pong game and this flash memory programmer. Working directly with microchips allows us to do smaller yet more powerful circuits and control much more freely the features, size and format of our project. Furthermore, many microcontrollers for which you will not find Arduino boards can be used and programmed with Arduino, and you can even, in the case of many other microcontrollers from this manufacturer, use this very same external programmer and way of doing things to upload programs to them.